How to design control systems with PID. Imagine you're trying to keep a car at a steady speed on a hilly road. You need a system that reacts quickly and smoothly to changes. That's where a PID controller comes in. It helps machines stay on target by adjusting their actions based on feedback. First, you need to understand the three parts of a PID controller. The proportional part reacts to the current error, which is the difference between what you want and what you get. If the error is big, it makes a big correction. The integral part looks at the sum of past errors. It helps fix any steady mistakes that the proportional part might miss. The derivative part predicts how the error will change soon. It helps prevent overshooting or oscillations by slowing down corrections when the error is changing quickly. Next, you set up a feedback loop. You measure the system's current state using sensors. For example, if you're controlling a robot arm, you measure its position. Then, you compare this to your desired position, which gives you the error. The PID algorithm takes this error and calculates a control signal. This signal tells an actuator, like a motor, how much to move or adjust. The control law is written as a simple formula. The output equals the proportional gain times the error, plus the integral gain times the accumulated error, plus the derivative gain times the rate of change of the error. You need to choose the right gains for each part. Start with small values and adjust. Increasing the proportional gain makes the system respond faster but can cause oscillations. Increasing the integral gain helps eliminate steady errors but can make the system unstable if too high. The derivative gain smooths the response and reduces overshoot. Tuning these gains takes some trial and error. You can use methods like the Ziegler-Nichols technique or simply test and observe. Watch how the system responds. If it reacts too slowly, increase the proportional gain. If it oscillates, lower it or increase the derivative gain. If there's a steady error, increase the integral gain carefully. Once you find a good balance, test the system under different conditions. Check how quickly it reaches the set point, how much it overshoots, and how long it takes to settle. Fine-tune the gains until the response is both fast and stable. In mechanical engineering, PID controllers are used everywhere. They control robot arms, regulate motor speeds, and manage temperature in manufacturing. Be aware that sensor noise can affect the derivative part, so filtering might be needed. Some systems prefer only proportional and integral control if the derivative is too sensitive. Also, implement anti-windup strategies to prevent the integral from growing too large when the actuator can't respond. By following these steps, you can design a control system that keeps your machines running smoothly and accurately. Whether it's a robotic arm or a temperature control system, a well-tuned PID controller makes all the difference.